Hello everyone, today I want to share the section in Display Weeks about OLED optics. The first part is polarized emission thin film light emission diodes. Diffractive optical elements have also been used to extract thin film optical modes for directional emission, and subsequently emitted photons are coupled into a thin film waveguide strip and extracted by the DOE pixel, yielding direction emission. However, the device efficiency is very low. Here, we demonstrate highly polarized light emission from OLEDs on grating substrate to selectively extract the TE waveguide mode by suppressing the SPP, TM waveguide, and air mode. The 3 steps to design a waveguide emission OLED. First, suppress the cavity emission as is in a conventional OLED. Second, couple light into TE waveguide mode into ITO anode. Final, couple TE waveguide mode out through corrugate substrate ITO interface. We use the finite different time domain method to simulate the electric field distribution of the optical modes in an OLED with a 140 nanometer ETL. The result confirms that the TE waveguide mode is located at the vicinity of the ITO node. Therefore, having a corrected ITO node will allow effective extraction of the TE waveguide mode by diffraction. To enhance the efficiency of the polarized emission device, the key is to increase the waveguide mode. We perform a simulation study on the mode percentage as a function of the EML index of refraction, and the results are shown in figure. For most OLEDs, the effective index of refraction is about 1.7 to 1.8. For a parasect, the index of refraction can be as large as 2.3. As a result, the TE waveguide mode percentage can exceed 40%. To achieve this emission characteristic, the coverage at the top cathode is prolonged by the thermal evaporation of the thick organic stack. This not only reduces the background air mode emission, but also suppresses the diffraction of the SPP and TM waveguide modes, resulting in polarized light emission from the TE waveguide mode having a TE and TM extinction radius of 30. We systematically analyze OLEDs made with an ultra-thin edge node, and found that waveguide modes can be completely eliminated by designing a structure to below the cutoff thickness of waveguide modes. We also experimentally rewrite the waveguide modes elimination in organic waveguides. The approach to mechanism of waveguide elimination is to use an ultra-thin edge layer. The schematic of OLED shows that waveguide mode TE0 and TM1, which are the 2 lowest order modes, typically guide in traditional ITO-based device. This is because ITO has the highest refraction index of all layers. In contrast, low-loss metals such as Ag has real part of the refractive index close to 0, therefore can drastically reduce the effective index of the waveguide layer. The figure shows measure current density voltage characteristic of the ITO and CUAG device. The 2 devices show very similar electrical properties, overlapping in the curves. This indicates that electrical property of OLEDs was altered by replacing ITO with it. Therefore, the EQE enhancement from it is purely an optical effect and the result of more emit phantom being coupled out of the OLED. The third subtopic is about use of DMD with thin edge for higher efficiency. Typical high-performance OLEDs have organic thickness below 150 nanometer. As shown in figure, the cutoff condition for the guided mode with DMD can still be satisfied for practical OLED applications. Both the waveguide modes are excited in the ITO OLED and experience significant energy dissipation in the entire emission wavelength, but the waveguide modes are only guided at short wavelength range in the DMD OLED with little trapped energy. In this work, we introduce a design strategy to ultralight high-performance thin edge-based transparent conductor by replacing conventional ITO with an ultra-SU edge thin. The total thickness of OLED is maintained thinner than the cut-off thickness for the formation of an optical mode of the layers, thereby suppressing the waveguide mode in the device. This simple and yet novel approach could pave the way to replace ITO and increase efficiency in flexible and transparent OLED that are widely used in display industry. In this paper, we explore energy loss in the novel plasmonic OLED device architecture that enable next-generation OLED operation by harnessing energy previously believed to be trapped in the plasma mode. The right figure is EQE versus current density for plasmonic OLEDs with either edge adhesion layer or edge adhesion layer 2. To investigate this matter, we measure the EL transition of both devices in figure left. Utilizing the EL transition result in EQE values, we can calculate the plasma in coupling efficiency. Here, tau is the experimental determined EL transition. This result indicates that the chief source of efficiency improvement by adhesion layer 1 can be attributed to the plasma out-coupling efficiency, which can be calculated. This calculation yields plasma out-coupling efficiency of 27% for adhesion layer 1 and 20% for adhesion layer 2, the ratio of which agrees with the greater than 30% EQE improvement discussion earlier. In summary, we have found that the choice of material for an edge exchange layer can have important effect on the device performance of plasmonic phones incorporating a nanoparticle-based plasma out-coupling scheme. By ruling out all other possible explanations, we conclude that the origin of the efficiency improvement is due to enhanced plasma out-coupling efficiency enabled by improved edge quality from the adhesion layer, as confirmed by simulations. This result underscores the ability of plasmonic OLEDs to extract energy from the plasma mode and represent a new paradigm of OLED operation. Further improvement to plasmonic OLED architecture are expected to double the efficiency of conventional OLEDs while increasing device stability by up to an order of magnitude. In this work, we examine the nature of reflective artifact in OLED display and show that diffraction of ambient light can account for a significant portion of the diffuse reflection. The background for the diffraction of ambient light to occur upon incident to an OLED display, there are two notable requirements. First, a wholly or partially coherent light source, and second, an absent or opening imparting differential behavior upon a propagation wave of light, like the figure shows. To demonstrate the effect of reducing the degree of effective spatial coherence, we capture equivalent image at progressively smaller distance separating the LED and the phone, like figure B and C shows. Examination of all three images in figure reveals that the degree of effective spatial coherence decreases. The aesthetic nature of the diffractive diffuse reflection changed from multi-state type to single-state type. For the left figure, we find that 12% of the incident light is reflected with 44% of the reflected light being diffractive, resulting in a diffractive reflection of approximately 5%. The second display component we analyze is a color filter. We find that results in a diffractive transmission of approximately 14%. To understand how the diffraction of these individual components can affect the diffraction within an entire display system, we find that for impact and conclusions, this is also the summary for all the video. Overall, we have presented a way to interpret the degree of effective spatial coherence for a typical ambient light source pattern when viewing an OLED display. In order to reduce the intensity of diffractive refraction, it is necessary to reduce the intensity of the gratings present in the display system. These findings have broad implications for how next-generation optical features are designed for OLED display.